Hello and welcome back to the next video in our series. Today we will be studying the Doppler effect. The Doppler effect is the change in frequency of a wave in relation to an observer who is moving relative to the wave source. It is named after the Austrian physicist Christian Doppler, who described the phenomenon in 1842. While there are many fancy definitions we can give to the Doppler effect, we're going to go right to the most common example of the siren that seems to change pitch when the ambulance is approaching you, and when it passes you, it changes pitch again. You may have been standing on a street corner once and you heard an ambulance coming, and as the ambulance approached you, you heard that the siren of the ambulance was very high pitched, and as it passed you by, that pitch began to change and lower itself and even blur and smear out to a duller, lower frequency, lower pitched sound. Well, we're going to demonstrate that with a FET. There's a very simple reason why that's happening. So the basic answer is this. As the source of sound emanates waves from its center, they're all concentric and the same distance of wavelength apart. But if the source is moving, then those waves crunch up on one side and stretch out on another. Let's take a look at that in the simulation. Here in the simulation, I have the ability to start the waves, and you can see the wave begin to emanate in circular wave fashion and then suddenly begin to move to the right of the screen. Let's take a look at this behavior. You can see that as the wave moved from this origin point along this yellow line on the left side to the right side, that the wave shape is no longer perfectly circular, like it would be if I just pinged a wave like this. So this is a pinged wave, and you can see it emanates in a circular fashion. Now our wave bounced off of this rightward point and is returning back to the left side of the screen. You can see something very interesting that's happening here, and when the wave returns, I'm going to stop the video simulation and I'll show you. Alright, it's going to return to the right side along this yellow line. Alright, here's a good place to stop. I think it's very clear now that you can see how the waves are different wavelengths on different sides of this yellow line around the source. Since this source is moving to the right, the waves that are in front of the source are compressed. And therefore, if you were to measure from black line to black line to black line, which are troughs, or measure from the highest, brightest point of the blue line inside this circular ring, that's the crest, crest to crest to crest, you would see that the waves on this side of the source are compressed and they have a lower wavelength. They have a lower wavelength, they have a higher frequency. On the left side of this source, you can see that the opposite is true. The source is moving away from these waves and thereby stretching them out. And those waves are stretched out, they have a longer wavelength and therefore a lower pitch. If you were standing right here, this red circle, as the source approaches you, the waves which are compressed have a higher frequency. So on a musical note scale that you'd find on a piano, you'd have a higher pitch. But if you were standing behind it and the source was moving away from you, then you would hear a lower pitch or a lower note on the piano. In essence, that is the Doppler effect. It's all dependent on where you're standing. To summarize, if you're standing in front of the source and it is approaching you, you will hear a higher pitch because the wavelengths are shortened and the frequency is raised. If you are standing behind it and it is moving away from you, there is a stretching of the wave, elongation of the wavelength, and a lowering of the pitch. So in essence, that's the Doppler effect. Very easy to understand. If a wave is being created by a stationary source, the wave is concentric on all sides of the source, and the distance from crest to crest to crest to crest is the same wavelength. But if the source is moving, in front of the source you have a reduced wavelength, therefore a higher frequency, and behind the moving source, if it's moving away from you, you have an elongated wavelength and therefore a lower frequency. Alright, let's take a look at an example problem. In the diagram below, a stationary source located at point S produces sound having a constant frequency of 512 Hz. Observer A, 50 meters to the left of S, hears a frequency of 512 Hz, but observer B, 100 meters to the right, hears a frequency lower than 500 Hz. What statement best describes the motion of the observers? And the answer is very simple. Observer A is stationary, and observer B is moving away. And how do we know that? If this is the sound source, and this person at A hears the same frequency as the source, that means that he is receiving the concentric rings of equivalent wavelengths, meaning he hears the same sound. But this person hears a frequency lower than 512 Hz, so therefore he must be moving away because he hears a pitch lower than the one that's being produced by the source of sound in this location. It's that simple. I hope you enjoyed this video, and I thank you for watching. We'll see you in the next one.